Um, Hemanth Dakshinamurthy. I'm sorry, I messed that name up. Okay, I'll let you say your name. Sorry about that. He's going to be talking about low-cost, fully automated, autonomous UAV-based soil moisture payload for near-surface measurements. Let you take over.
And when you click on this arrow or that arrow to go back or forward.
These are small board.
They do not work.
Okay.
I don't know why.
Okay. Good morning, everyone. I'm Hemanth Dakshinamurthy, research scientist from South Carolina State University. I'm here to present about a low-cost, fully autonomous UAV-based soil moisture payload for near-surface measurements. This is going to be slightly different from other talks that you have been hearing across this workshop, but I hope it's interesting, and I'm looking forward to learn your feedback and comments on our work. So, importance of near surface soil moisture. Probably this is one set of audience where I can skip this slide because I hope everybody here in one form or another knows the importance of near surface soil moisture. So I'm confidently moving to the next slide. So common approaches for soil moisture measurement. So the existing techniques we have are gravimetric technique, where we walk across the field, collect soil samples, go back to the lab, measure soil moisture, or we establish a soil moisture sensor network, and we get continuous long-term data. And then we have remote sensing, where we use satellite products or drone images to model our soil moisture. So I would like to highlight a word which is common in all these techniques, that is field specific. So what we mean by field specific here is your soil samples that you collect in gravimetric technique, the sensor networks, the data you get, or the remote sensing models you build are all field specific in nature. They are not easily transferable to any new field that you want to work in. So we identify there is a gap over here. Can we provide a field agnostic solution where we can address this challenge that scientists or farmers or any stakeholder faces? So why do we need a soil moisture payload or a UAV-based soil moisture payload? So we present a scenario where we have to measure soil moisture from n different spots from multiple agriculture fields for multiple days. So what are the options that are available to us? So the solution we provide is a fully autonomous UAV soil moisture payload. So we had two versions which were built across my PhD thesis, version 1 and version 2, where we were able to refine our payload models. And now at SE State, I'm building version 3. So what's new in version 3 is it's a lower cost, because we have reduced the cost by $500 by replacing our microcontroller from MyRio to Raspberry Pi. And it's going to be fully built on open source. We are going to have real-time dashboards. We are going to have user-friendly controls. And we are also going to have real-time soil moisture corrections from our payload measurements. So this is our system architecture design. I'll just keep it very simple. We have our UAV payload designed in a way where we want to do our soil moisture measurements when the drone lands. And we pre-code our GPS coordinates, but we want to extend a system where it's user interactive, where the user can provide the GPS locations where they want to measure soil moisture. And we do 3 measurements at each sampling location. So when the drone lands, we would insert the sensor 3 times in that locations, and we will also record the TDR waveforms. And we have the Arduino to do the controlling job, and we use the Raspberry Pi as a computer to save and to create the real-time dashboard. So this is a quick video of the version 3 in operation in South Carolina State University. As you see here, I will not control the drone when it lands. The drone will land on its own, where it is going to land at the described GPS coordinate. And once the drone lands, you will see it senses, the payload senses the drone lands, and it will start inserting the soil moisture sensor into the soil. And it will also record the depth and the TDR waveform. So this is a fastened version to reduce the memory and also to not bore you guys, because at each location we do 3 insertions, and 3 insertions together take 10 minutes. It's kind of slow, I understand, but the reason to have it slow is the slower you insert the sensor into the soil, the better is your full insertion chances. So that's why I keep it slow and for the safety purposes as well. So coming back to the most important question, can this payload be useful? And that's where I'm really all ears for the different stakeholders we have over here. And one way we thought of testing this out is we wanted to compare two sampling strategies to understand a spatial variation across surface soil moisture in a agriculture field. So we are comparing two sampling, that is grid sampling and condition Latin hypercube sampling, or we want to term it as smart sampling, across two experimental sites. One is in Florence, USDA Florence, and another one is in South Carolina Research and Demonstration Farm at Olar. And our hypothesis is that smart sampling would be better than grid sampling to understand spatial variation across a field with minimum number of points. So we have identified sampling points by providing wetness index, normalized difference moisture index, and elevation across our research sites. And we were able to generate condition Latin hypercube sampling points for our research site. The black line is our research site. This is in Olar. For different number of sampling points, we finally decided 12 sampling points is ideal to test the drone and also to verify the accuracy of the data that we are collecting. So we have 12 CLHS sampling locations at Florence and 12 at Olar, and we also have 12 grid sampling locations at the same time. So these are our snippets from our data collection at these test sites. As you can see over here, we are testing in a big area this time, and we encounter several different landscapes, from dry sandy soil to wet sandy soil to a location where there is tall weeds left over, and on the right you see leftovers from cotton harvest in USDA ARS site. So these are our preliminary results from our data collection at Olar in May 2026. We see good agreement between manual insertions and automatic drone insertions. Please note, we have not done any corrections to our drone measurements. I think with corrections, our correlation is going to improve with the manual data. And we are also collecting soil samples, and also we are going to compare the accuracy of our drone measurements and manual insertion measurements, which will be getting soon. Our future research is to complete our test our hypothesis and in the two test sites, and hopefully we'll be able to come up with a solution where we can confidently say, hey, these are the minimum number of sampling points you need in a given area to measure soil moisture. And hopefully I see if I get good positive feedbacks from different stakeholders from this workshop, hopefully in future, I hope to see this payload in each one of your labs, and you guys are using it for your soil moisture measurements. And we are also trying to modify this from drone. We are trying to modify this to put it in any vehicle you have, be it a Ford F-150 or a tractor or a Gator. So that's our next step. But that's the vision I have. Hopefully you guys have positive feedbacks for our project. So I would like to thank South Carolina State University, USDA Florence, for allowing us to work and collect data from their site. And this is my contact information. So thank you.